A value for enthalpy of solution can be determined in two ways. From a cycle using lattice enthalpy and enthalpies of hydration, or from the results of a calorimetry experiment. Define the term lattice enthalpy of dissociation. So what we're trying to do here is take an ionic lattice, so for example sodium chloride, that is in the solid state and completely overcome any forces of attraction that hold it together. So we're going to turn it into the ions that are in the lattice, but we're going to overcome all the forces, and so they're going to become gaseous ions. So we need to be clear about what we mean by enthalpy change. So an enthalpy change is a heat energy change at constant pressure. And then we need to say what lattice dissociation is. So it's the heat energy change at constant pressure. You could, at this point, probably have just said enthalpy change, the heat energy change at constant pressure when, important part, 1 mole of, because it's per mole, and per mole of what? It's per mole of the solid ionic lattice dissociates, breaks down into gaseous ions, and that gaseous is another really important part. The enthalpy solution for ammonium nitrate is the enthalpy change for the reaction that's shown below, where 1 mole of the solid ionic lattice becomes aqueous ions, and it says that it's got an enthalpy change of plus 26 kilojoules per mole. Draw a suitably labelled cycle and use it. So we're being told we must draw a cycle and not just use an equation, and label it with data from table 1 to calculate the enthalpy of lattice dissociation for ammonium nitrate. So there are many ways to draw this cycle. We've been given a value for an equation above, so we could use that at the top of the cycle. Or we could have put the enthalpy of dissociation at the top of this cycle. That's the thing that we are trying to calculate. Now it's telling us that this arrow is worth plus 26. We're trying to calculate lattice dissociation, which is when 1 mole of this solid ionic lattice breaks down into gaseous ions. Now state symbols are very important in Hess cycles because changing state takes energy. So it is really important that we put these on. This is our unknown, X, the one we're trying to find out, the lattice dissociation. We've been given hydrations, and hydrations are when gaseous ions become aqueous ions. So we've got the ammonium ion, minus 307. We've got one of those, and then we've got the nitrate ion at minus 314. Now, according to Hess's law, if I want to find the value of arrow X starts here and ends here. And we want to find a different route. So the other route would be to go round our cycle in this direction, the longer way around. So X, our short route, is equal to, we're going to follow the first arrow, so plus 26, and then we're going to come backwards against the sum of these hydrations. It'd be a good idea to add that bracket up, particularly if you struggle with expanding brackets, because you've got minus numbers in a bracket with a minus in front of it. So the total of that bracket is minus 621. So we're going to minus a minus and it becomes a plus. And then we add it to 26, we get plus 647 kilojoules per mole. Student does an experiment to determine a value for enthalpy of solution. So remember, we were already shown that the enthalpy of solution was when we went from the solid ionic lattice to the aqueous ions. We would do that by adding water and dissolving it. The student uses this method. They measure 25 centimetres cubed of distilled water in a measuring cylinder and pour the water into a beaker. So they've put 25 centimetres cubed in here. They're recording the temperature of the water in the beaker. They add in 4 grams of NH4NO3 and stir and record the lowest temperature reached. What that means is if the temperature goes down, that the reaction is endo and delta H is a positive answer. Well, we knew that anyway because we've had a value up here of plus 26. I'm going to go down to the line though and write it on the line now, the plus, because it was endothermic, so I don't forget later on. We can work out our temperature change here by doing 20.2 minus 12.2, and we're getting 8 degrees. It says calculate the enthalpy solution with this experimental data, given that the specific heat capacity C is 4.18 joules per Kelvin per gram and the density of the solution is 1 gram per centimetre cubed. So therefore 25 centimetres cubed must be equivalent to 25 grams. So I'm going to calculate the heat energy released or gained when, in this case gained because temperature fell, when we added the ammonium nitrate. So it was to the 25 grams of water, 4.18 was the specific heat capacity and 8 was our temperature change. This is going to give us an answer in joules, and that's because 4.18 is in joules per Kelvin per gram. To calculate delta H, which is a number in kilojoules per mole, we need to take Q, turn it into kilojoules, so I'm going to divide by 1,000, and then divide by the number of moles of ammonium nitrate we used. So we're going to need to work out the number of moles of ammonium nitrate by doing mass over MR. We used 4 grams, and we need to add up the MR of ammonium nitrate. So we've got 2 14s, a 4 and 3 16s. Use your calculator, you can see that that adds up to 80. And that is 0.05 moles. So we're going to take our 836, divide it by 1,000 to get it into kilojoules, and divide it by the number of moles we used to get our enthalpy change. And that is coming out as 16.72. We could give that to 3 significant figures or leave it. We haven't been asked for appropriate significant figures. So 16.7 or 16.72. That's our enthalpy change. The uncertainty of each of the temperature readings from the thermometer used is 0.1 degrees C. Calculate the percentage uncertainty. So we want to take the uncertainty and divide by the reading and times by 100%. But we've got this word each and we did 2 thermometer readings, so we'll need to double our uncertainty. So we're going to go 0.1 doubled. Our reading was 8 degrees. So we're going to do that on our calculator. And we're getting 2.5% as our percentage uncertainty. Suggest a change to the student's method using the same apparatus. So we can't change the thermometer, which means we can't change the uncertainty on the top line of this calculation. That means we need to increase the reading on the bottom line in order to get a larger temperature rise. So we need some way of getting a larger temperature rise that will reduce our percentage uncertainty. So given that our experiment was just adding solid to water, if we want to get a bigger temperature change, we need to use more solid, more chemicals. So in this case, it was a mass of ammonium nitrate. By using a larger mass, we will get a larger temperature change. And as a result, the percentage uncertainty will decrease. So another student got a value of plus 15. So remember, we got plus 16.7. The actual value was plus 26. What that means is that when the experiment happens and there's no errors, that more heat is absorbed by the chemicals from the system, and that we get that bigger value of Q. So we get a bigger temperature change, and as a result of getting a bigger Q, we get a bigger delta H, a larger value. Why might that happen? Now, the temptation here is to just immediately write heat loss to the surroundings, but that's not appropriate because this one did not lose heat from to the surroundings. This gained heat from the surroundings. So instead of heat loss, we would need to say heat gain from the surroundings. So instead of taking it from the chemicals, it was taking it from the surroundings. Or if you think about this experiment, there's a really good chance that not all your solid dissolved, and therefore you didn't get as large a temperature change as you should have done. There's a really good chance that would happen. Table 3 shows some entropy data. Remember, entropy is a measure of disorder. Calculate a value for the Gibbs free energy for the reaction when ammonium nitrate dissolves in water. Use data from table 3 and the delta H from the equation. Assume for the solvent water that the entropy change delta S is 0. Now here we need to do delta G equals delta H minus T delta S, and we want T to be 298K. We've been told that delta H is plus 26, but we haven't got delta S other than for the water. We need to calculate delta S by doing, it's the sum of the entropies of the products minus the sum of the entropies of the reactants. We want to know how much the entropy changes during this reaction. So the products being 1 ammonium ion and 1 nitrate ion, and the reactants being 1 ammonium nitrate. So on your calculator, you're going to add that and subtract minus 151, and you get an entropy change of 108. But remember, we're doing the adding up entropies, so that's in joules per Kelvin per mole, and delta H was in kilojoules per mole, so we need to be careful. So delta G equals delta H, 26 kilojoules per mole, minus 298K temperature, times delta S, but we want to convert it into kilojoules per Kelvin per mole, so we're going to divide by 1,000. Typing that on our calculator, so 26 minus 298 times by 108 times 10 to the minus 3, that's the divide by 1,000 step. That's going to come out on my calculator as minus 6.18. So delta G is minus 6.18. Now, because that's a negative value, so since delta G is less than or equal to 0, it's a negative value, the reaction is feasible at 298K. If delta G is negative, then the reaction is feasible at 298K. Ammonium nitrate decomposes as shown. The entropy change for this reaction is 144. Calculate the temperature at which it becomes feasible. So it's going to become feasible at that flipping point. It's not feasible when delta G is positive, and it is feasible when delta G is negative. So if we set delta G to 0, that would be the point at which it becomes feasible. So 0 equals 123 minus a temperature times 144. But remember to convert these units. They're not the same, so we need to convert. So I'm going to add T times 144 times 10 to the minus 3 to both sides. And then I'm going to divide both sides by 144 times 10 to the minus 3. And we get 854 Kelvin. So we just write that on the line. If this had been in degree C, we would have had to do a conversion at the end.